Hello and welcome to my basement. We're here to do some work with the central limit theorem. So let's get right to it. The central limit theorem is broken up into a couple of different flavors. We're going to be using just the central limit theorem for means. And this is a way of comparing, of taking data from a large sample and comparing different samples together. So if you can think of one way you can think of this is that a normal curve. So we're going to take data from a bunch of samples and put them into a normal curve. And if you took individuals and put them into a normal curve, you'd get, well, the normal curve you would expect. But when you have a bunch of samples and put them into a normal curve, then you would end up with a different normal curve. Anyway, the couple of things that we need to note is that the size of the sample needs to be large enough to make things work out well mathematically. We're not going to get into the details, but rule of thumb is that the sample size should be at least 30. Now it's at this point that I would be having you rolling dice, but I'm not having you roll dice because that's just the way it is. But I can show you here just a sec. Not there. I can show you my dice example if you give me a sec. So should have had this up, but I didn't. There it is. I think this is it. We're going to find out. Oh, here we are. Okay, so if we were to roll dice, and if I were to have you each roll one die, then you would expect, now this is a fictitious class of 1,000 students here. We would expect that about a sixth of you would have a roll of one, a sixth would have a roll of two, and so on. Things get interesting when we have you roll the die 10 times. So let's see what happens if I make this fictitious class roll the die 10 times and then average their rolls together. You can see that this ends up resulting in something that looks roughly normal. It's not quite normal, but we could do this again. And with 20 rolls, and it gets even more normal, and so on. So if we had done this as a class, I would have had you each roll the die 30 times, and we would compare all of our means, and we would actually get a curve that looks something like this. This class of 1,000, though, I can make them roll the die over and over again. Each time you see it's pretty much a normal curve, and it's pretty much as spread out the same each time, centered at the same place. And that's what the central limit theorem tells us. It tells us the relationship between how many times you roll a die and where we should expect this normal curve to end up. So if we roll this 20 times, notice that it's spread out. When we roll the die 100 times, it's more compressed, compact. So let's get back to our PowerPoint. The central limit theorem basically just says that if you do something over and over again and average together the results, what you'll end up with, if we all do the same thing, then the distribution is called a sampling distribution. That is to say, I will do a sample of 100 rolls of the die, you will do a sample, your brother will do a sample, everybody does a sample, and we compare our averages. That's a sampling distribution. And the sampling distributions of means is normal, and turns out that the mean does not change, but the standard deviation does change. And this is to be expected because the more you roll the die, the more similar you're going to be to someone else rolling the die. So here is the general idea. If we all roll the die once, I have over here in the sort of peach colors, I have the mean and the standard deviation of this distribution. So notice the mean is 3.4. It should be 3.5, but it's 3.4. And the standard deviation is 1.7. When I roll this 100 times, according to the central limit theorem, what should happen is the mean should stay the same, but the standard deviation should be reduced by a factor of the square root of 100. I hope you know the square root of 100. If you don't, I'll tell you, it's 10. So this should be reduced by a factor of 10. Let's go ahead and see what happens. Sure enough, we went from 1.7 to about 0.17. Here, let's just take a look at this again. Here's 1.7 and then about 0.17. Notice that the mean stays about the same, 3.5, 3.5, close enough. If I roll the die 25 times, we should reduce the standard deviation by a factor of 5. So the central limit theorem just says that you reduce. So this is a little harder to tell, but if you take 1.7, divide it by 5, you get 0.34. Okay, so getting back to this, how are you going to do this for your homework? Well, let's start with this. An unknown distribution is created by the test scores of a nationwide standardized test. This distribution has a mean of 90 and a standard deviation, sigma, of 15. Sample size is 35. So the new mean will be the same as the old mean, which is equal to 90. That is to say, if we were to all, like every one of the people in our class, if we were each to take a sample of 35 people and did this standardized test with them, we would find that the mean of all of our samples is the same as the original mean, which is 90. However, the new standard deviation is the old standard deviation divided by the square root of n. In this case, n is 35. So this will be 15 over radical 35. So that's going to be half of your homework right there, is just computing this. Let's do another one of these just to make sure that you see how this works. So let's say that we have an unknown distribution with the birth weight of males, and it turns out that the mean of males is 7.8, and the standard deviation is 1.2 pounds. Sample size is 130. So the new mean, which I'm going to label like this because that's the way it's supposed to be labeled, that's the new mean, is the same as the old mean, 7.8. The new standard deviation, whoa, not that. Here we are. Come on, buddy. So the new standard deviation is the old one divided by the square root of n. And so in our case, it's 1.2 over the square root of 150, whatever that is. Now for something that's actually somewhat important. Well, actually, this is all important, but let's take a look at this problem. What is the probability of finding a sample with a mean larger than 8 pounds? To do this, I'm going to use Microsoft Excel. I believe that your homework at certain places will ask you questions like this, and it will want you to use a table. You can use Excel. So just use Excel. So here's my Excel. Now I'm going to have to sort of toggle between these things because I'm also going to show you this that I forgot to show you last time. So this is just a little Excel spreadsheet that I made that will allow you to make a nice normal curve with the shaded area like we did last time. So if you remember the mean of our sample, it was, here, let's switch back here, 7.8. And then the standard deviation is 1.2 over the square root of n, square root of 150. So we'll do 7.8 for the mean. And then what do we have here? 1.2 divided by the square root, squirt. Oh, I need to actually type an equal sign. 1.2 divided by the squirt of 150, which is that. Now the A and the B, what those represent are just, if I was going to make, you can see the numbers along the bottom there. If I wanted to do something like this, go from 7.5 to 7.9, you can see that there it's shaded the appropriate region. Maybe it would be more exciting if I did 7.6. Okay, there, that's a little bit more exciting. Okay, so going back here, the problem is asking for the a sample greater than 8 pounds. So what I'm interested in is I want to know the probability that x is greater than 8. Remember that Excel is leftist, and so instead of doing greater than 8, we're going to have to do less than 8. But on my little diagram on the left, I can actually just put 8 there, and then maybe 100 or something there. So you can see the shaded region. This is what you would get if you were to do this on a piece of paper. You'd have this little sliver. What's that, 3-4%? I don't know. But in Excel, we're going to have to do the probability that x is less than 8 first, and then we'll subtract from 100%. So this is going to equal norm.dist of, let's see, 7 point, no, wait, the x is 8, the mean is 7.8, the standard deviation was 1.2 divided by the square root of 150, and I truly want to know the answer. So that's that, and now we do equals 1 minus this to get the area to the right. So I'd guessed about 3%, I was off, it's actually about 2%, but still, that's pretty good. Okay, so let's try one more of these just to see how this works. So you can do this yourselves. Let's see, the average number of grams of gold per million tons of seawater, whatever that is. Anyway, let's see, the distribution has, this is kind of a dumb question. Is there anything better than this? Yeah, let's do this one. Yeah, I don't like that one. Let's do this one. Wait, that's confusing. Don't I have any, here we go. We'll do this one. Okay. Good enough. Yeah, I guess I have a lot of repeats here as I'm looking at my my PowerPoint. It's weird. Okay. Well, anyway, let's just barrel on ahead here. It says that we have a mean of 90. This is familiar. A standard deviation of 15, and I want to find the probability of being between 85 and 92. So we have the new mean, and we did this already, I believe, and the new standard deviation is 15 over the square root of 31. And I'm trying to find this probability. So let's just go ahead. We'll do this on both of these. Let's see. First of all, the mean is 90. This is equal to the, 15 over the square root of 31. Ooh, that's not right. This is supposed to be 15, not S15. There we go. That's better. And I want to know, let's see, we got 95. Yeah. Okay, so I want to know between 85 and 92. Okay, there, that's a nice picture. 40, 50%, something like that. So let's go get the other Excel. Here we go. And so you remember that if you need to go between two numbers, what we're going to do is we're going to do the probability that x is less than 92, and then I'll do the probability that x is less than 85, and then I will do the probability that 85 is less than x is less than 92 by subtracting those two. So this is going to equal norm.dist of 92, 15 divided by the square root of 31, and true because I truly want the answer. And then I just copy that down there so I can just change this one number, 85, and then this will equal this minus that. There you go. Just a couple of things to note about the homework is that you'll be doing some of this. Like I said, there's some that ask you to use a table. Just ignore that. Use Excel. It'll work. And then the other thing is that there will be a few normal curves that you'll have to deal with. Let's see. I think I've got this on here. Okay, cancel. Let's just preview this as a student. Give me a sec. I'll pull this over and you can see what I'm talking about. Okay, so here's a good example. So it says that we have $50 is the mean, standard deviation is 16, but we're going to do a random sample of 35. So what we'll need to do is, first of all, the new mean is the same as the old mean, which is 50. So we move this over to 50. And then the new standard deviation is 16 divided by the square root of 35. So I need to do that over here on a calculator. 15 divided, or 16. 16 divided by the square root of 35 is 2.7. So let's see, 2.7. This is a little bit annoying. Oh, I got it. Because it doesn't seem to work well with the mouse, but do your best. Basically, you're just computing the new mean, which is the same as the old mean, and the new standard deviation to get this. And then you've got that. Beautiful. So yeah, it even tells you that. And so here's the business with the table. So I want a sample size will be less than 55. So over here we're going to do equal to norm, norm dot dist of, what was it? Sorry, I have to remember what the original thing was. 50. Okay, so we want to know 55, 50. I probably should have typed my math first. Let's see, it was 16 divided by the square root of 35. And then we truly want the answer. And the one thing I need to, just a minute, let's copy this because I'm a little concerned. Just a minute. Let's change this to 2.7 and see what kind of a difference we get. Okay, it's nearly the same. I think that they're going to want you to use the 2.7 rather than this. So let's find out if we can just do this. If not, I'll show you the right answer. So this is 0.9679. Let's see, let's try. So 96, do I round? Nearest percent. Oh, it won't matter then. 96.79. So 97%. Good. Oh, good. Yeah. So just in case it doesn't work for you, what you will need to do is compute the z-score for 55. So let's do that. The z-score for 55 is 55 minus 50 divided by the standard deviation, which is 2.7. So that's 1.85. And you would go on this table and you see here's 1.8. And we go over to 1.85. Whoops, there it is. So 1.85 is 9678, round that, 97%. So, oh, look, they even highlighted it there. So hopefully they'll round everything so that it won't matter if you use Excel, but just in case, that's the way that works. All right, I hope this works for you. And hopefully you have a good snow day, and we'll see you on Wednesday. Oh, don't forget to look over the practice test. We'll talk about that on Wednesday.